Okay, so the last few weeks we've been talking about limits, and which is the intended height of a function. Loosely, the intended height of a function is you're getting infinitely close to a given x value. Now we're going to start working with derivatives, and the purpose of finding the derivative, this would be the notation dy over dx, and then later on f prime of x or y prime. All three of those will be accepted, but for right now I'm just going to have you use the standard derivative notation dy over dx, and the derivative is the function, which could be a constant, by the way, constant function, that produces the instantaneous rate of change. Remember what I mentioned before in the last video? Think slope of the tangent line, because it can touch at any given point and you can have an infinite number of them. So instantaneous rate of change at a given x value, and that, or sometimes they'll say c value, which is an x value. And that's important because what we're checking for, let's say you have a graph that looks something like this. Well, let's say these represent a bunch of values on the x-axis. Well, as you know right here, that slope is 0. That slope is not 0. So at any given, that slope is a negative slope, that slope is a positive slope, this slope is a positive slope. So the derivative is the function that produces the instantaneous rate of change. And what I mean by produces, once you get, let's say this is the function 2x and our leftmost point is 1, you would plug 1 into the derivative, and then you would see that the instantaneous velocity or slope of the tangent line would be 2. So let's go ahead and get started. But before we do any of that, I need to show you using the definition of a limit, or the definition of a derivative. So you used to do what's called the limit process in finding the derivative. And it says the limit as h. By the way, h and delta x are kind of used interchangeably. So sometimes you're going to say f of x minus delta x subtract f of x all over delta x. It means the same as if it says h. What that means is if you got an x-axis and this is your c value, and this is the, let's pretend this is infinitely close. Well, this distance right here is either h, or you can call it delta x. That's what we're talking about. All right. So to find the derivative, you do the limit process of f of, that's a plus sign right there, x plus h, the function of x plus h, subtract f of x all over h. And this is what that would, how we would apply that. So here we have dy over dx is the limit as either h or delta x approaches 0. And now we use this function everywhere there's an x. So right there, we're going to plug in x plus h right there. So we're going to plug in, so negative 2 times x plus h plus 3. So it's that entire function. Let me So negative 2 and then we subtract the original function. Well, what's the original function? The original function, we subtract all of it, so you put in parentheses, and then all of that is over h. So now we're going to simplify. So dy over dx equals the limit as h approaches 0. So negative 2 times x is negative 2x. Negative 2 times h is negative 2h. So we've done that distributive. And we still have this plus 3. Now we're going to subtract. Well, subtract a negative is adding a positive. So add 2x. Subtract 3 is just subtract 3. All of that is over h. And now we're going to simplify more. So we're going to see if there's anything we can combine or cancel. There's a negative 2x. There's an h, a 3. Positive 2x. So those cancel each other out. And what else do we have? We have a negative 2h. In the numerator, there are no more h's. We have a positive 3 and a negative 3. Those two cancel. And so now what you have left is negative 2h over h. The h's cancel. And because we now know what the limit is, remember, the limit of a constant is the constant of the limit. So now, since we know that the limit is this, we only did the limit process to actually find the instantaneous velocity. So there you have it. Now the limit process goes away, and as we get infinitely close, as h gets infinitely close to 0 at exactly that instant, or approaching that instant, the slope of that line will be negative 2. And then all you'd have to do, if you were going to graph this, negative 2x plus 3. So we're going to go up 1, 2, 3, and then go down 2 over 1, down 2 over 1. And look at the slope of that tangent line right there at that instant when x is equal to 0. Look what that says. That tells us that the slope is negative 2. So we did that correctly. Okay, this one is a little bit dicier. I don't know how much time we just left out. We just wasted. But anyway, this one's a little bit dicier. Notice this is a quadratic. So its graph, we're going to go up 5. 1, 2, 3, 4, 5. But at any given point, what will that slope be? Some of the lines, the slopes will be going downwards, some of them will be going upwards, and some of them will have, at one point, it will have a 0 slope. So let me cover that up. That h is not supposed to be there. So we're going to say dy over dx and right there with that first x, it's f of x plus h squared plus 5 minus f of x, which is 3x squared plus 5 all over h. Well, now you have to take the time to square this. Remember, if there's x plus y, it would just be x squared plus 2xy plus y squared. Well, that's what it's going to be, except for the y will now, there'll be an h involved because it's x plus h. So now what we have is, I'm going to do that and pretend that I just wrote all that. It's 3 times the x squared plus 2xh plus h squared plus 5. We're going to subtract the 3x squared, subtract 5 all over h. Okay, figure out what can cancel. Well, first we'll do the distributive. That would give us a 3x squared. Well, that 3x squared is going to cancel with that 3x squared. And then I'm going to kind of do it that way since I'm running out of room here. And then this 3 times 2xh is 6xh. Are there any other xh's? Nope. And then this 3 times h squared will be plus 3h squared. Then there is a plus 5. Oh, and there is a subtract 5. We already canceled the 3x squareds, and now the 5's can cancel. And all of that is over h. Now, what does 6xh, 3h squared, and h all have in common? They all have an h. So I'm going to factor out an h in the numerator, and that will leave 6x plus 3h. And in the denominator, those cancel. So now what we have here, I'm going to cover this stuff up. Now what we have is dy over dx is equal to the limit as h approaches 0, this function, 6x plus 3h. Remember what I said in the definition? The derivative is the function that produces instantaneous velocity or slope of the tangent line. So now we're going to substitute 0 in for h. Well, that will be 3, 0. So the function that's produced, is 6x. So dy over dx is the function 6x. So that's the derivative. And at any given time on a function, let's say at 1 second or 6 seconds, or if you're doing something else, you plugged in -5, you would know the instantaneous slope in that moment. All right, that's it for the definition of the derivative using the limit process.